Oh, you want me to make it a sticker? Yes.
Okay. So we should start. I know you have classes just before, so I know you need your 15 minutes or a bit more of Ausleitning, relax. Yes. And so it's fine. Right. But now we need to start. What we're gonna do today is we're gonna be starting to work from the verbal theories that we discussed last week into formal models. But let's take things one step at a time. Last week, we did an introduction to cognitive modeling, both the course, the exams, how we're going to do in lectures and classes, but also what is cognitive modeling. And we then spent the whole class playing a game, the matching pennies game, and discussing what might be the underlying cognitive processes and strategies that participants might employ when they play this game. And this week, I'm going to do a very brief recap of the key points of those. And then we're going to go into a very concrete example of how we formalize generative models of cognitive agents. And after trying a few different formats in previous years, the one that seemed to work best before is that I actually go through the process of coding up some of these agents. If the pace is too slow or too fast for you, just let me know and we adjust, right? Every class, every cohort is different. And so it's fine to adjust things according to where people are. We're not going to do the Bayesian recap until we're actually going to start inference so that I sort of first make sure that we're all at the same pace. Good. So what did we learn? Key ideas were that as we study cognitive science, we often observe behaviors. And we try to reconstruct the cognitive processes and structure that produce these behaviors. In data science lingo, the data generating process, right? Not the description of the data, but a mechanism that might be generating the data that we see. We discuss that we can formalize these processes, for instance, learning, right? As we're playing the matching pennies game, we try to learn how the other is playing so we can do the opposite of what they expect us to do. Or if we want to be very clever, the opposite of what they expect us to expect them to be doing. And by formalizing these processes, we can help our own understanding of the behaviors and compare and develop different models. And that as we will develop throughout this course, and probably you have started seeing in previous courses, there are structured workflows, that is structured practices, guidelines, and ideas on how to make these formalizations manageable, right? To help you along the way. You have steps that have been explored before, so you can rely on that. Also transparent, so other people know the way that you ensure that your model is meaningful. And also stress test. As we will see, lots of the models that we can think of actually fail miserably at describing the data and producing knowledge about the phenomenon. They help us understand modeling, but not as much the phenomenon. And we want to identify those cases and know how to stress test these models. Also, a very key aspect of formalizing models, right? Turning them from a vague theory built with words. And I want to specify words are actually very important in the modeling process, but so is algorithms and math. Right? By formalizing these models, we are better able to put our thoughts and science out there, make it open to critique, falsification, and community development. Right? For instance, we will see that theories of categorization in the later part of the course will make a lot of sense when we read the verbal descriptions, but as soon as we look at the formalization, we realize that they don't deal, well, the theories we'll discuss, they will not deal with learning the categories. They will all have expected you to already have learned the categories, which is not good if you're trying to use that model to describe an experiment in which participants have to learn new categories. If we had just read the verbal parts, we wouldn't have realized that that's a key part that's missing on the model. There's reasons for which that's missing, but that being formalized, we can take it and change the model so that it reflects our conceptualization of the problem. And we made a contribution to the thing. Or we show why, if we introduce model learning in that model, the model doesn't work anymore. And therefore, we need to think about the problem in a different way. Blah, blah, blah. Community development of science, right? So with that kind, are there questions on these ideas on cognitive modeling? There's lots more on cognitive modeling in the video. For those who came in later, in the video from the lecture from last week, which is linked on Brightspace. As we went through the class, we played the magic pennies with each other, and we started trying to figure out how can we describe the data generating processes. And we discussed a bit that there are some things that we can introspect as participants, right? We have certain ideas on how we play the game, but some things that we might not be as aware as participants, like what are the constraints of memory, right? We're not as aware of how many trials in the past we can remember, or how fast it decays. And so as we build cognitive models, it's important to both try out the phenomena that we're trying to study to get your EMIC. In the old social sciences, they would say the internal perspective on the phenomenon, but also sort of being able to zoom out as a researcher and say, we also know additional things from our cognitive science studies, for instance, that can help us build models of the data generating processes that the participants might not be aware of. We discussed possible strategies. I shared a PDF with all the strategies that were developed, also on Brightspace, but some examples were, simply random, where people might be biased in the randomness. So they're 60% of the times hiding the penny in the right hand if they're right-handed. Or it might be perfectly random, that is 50%. These might seem a stupid strategy, right? Both because we're terrible at randomness, but also because, of course, you can come up with a better strategy. But it really, in many contexts, like the best you can do in terms of performance. But we'll explore that when we play with it. A second approach is to include some sort of memory approach, where you can have a very extreme memory, which is only based on the previous trial. And There are strategies called win, stay, lose, shift, or win, shift, lose, stay, which embody that kind of idea. That is, if I play right and I win, I will keep on playing right. If I play right and I lose, I shift to left. That's the win, stay, lose, shift. Or, I might expect my opponent to think that I do that, so I'm gonna do the opposite, right? If I play right and I win, I'm gonna play left. If I play right and I lose, I'm gonna keep on playing right. The win, shift, lose, stay. We can have a more intermediate approach where the agent can remember any previous trials. For instance, we can say, well, let's look at the last 5 trials. How often has the other participant played right? And then we can take that as our expectation for when the other is going to play right. How big is N? That's a big tricky thing, right? We could implement what we know from cognitive science papers, or we might try to build models that actually try to estimate how far back in the past we reach. For instance, as you all know from Intro to CogSci, which I've recently censored, so it's very fresh to me now, exponential decay is one of the things that we know about how memory works, right? That we forget very fast, but then the forgetting slows down with a long tail. And there is a fantastically, it's one of the best cognitive models there is, really, reinforcement learning, which with a clever formula, which we'll see in a bit, allows you to actually have a term, learning rate, which can be estimated from the data, and it tells you how steep the exponential decay is, the rate of decay. We also discussed that as we play these games, we often try to be strategic, right? We don't just treat the other participant as a number generating machine, right? We're not trying to just learn the regularities in what the other person is doing and following them, but we conceive of them as agents in the work. That is, we try to infer their intent and mental states with what we usually call mentalizing or theory of mind. That is, we try implicitly or explicitly to formally represent the other as an agent in our own cognition. And we're trying to be very clever, as I was anticipating before, we might try to represent them as an agent, which tries to represent us as an agent, which tries to represent them as an agent, which tries to represent us as an agent, and so on and so forth, right? And as you'll see in one of the readings, these kind of problem has haunted a lot of the logicians and philosophers of language, and on how do we think about recursion and where does recursion stops. And from a cognitive modeling perspective, as soon as you start modeling in a formalized way these processes, basically all the models that I've ever implemented beyond 3 levels of recursion, so I represent you representing me, representing you, it just becomes too uncertain in the possible inferences, and the behavior becomes indistinguishable from lower level recursions, which is a nice consequence of formalizing the models. It says, given the models that we have, the problem is solved on its own. It doesn't make sense to go beyond 3. And lo and behold, is what most humans do. Yes, then we discussed the distinction between decision function and estimation, which I think you covered in decision-making last semester. That is, I might estimate the propensity of my opponent to play right. Once I've estimated that rate, I have an expectation about what they're going to do, about what Anton is going to do next. But then I have a decision-making process that might not necessarily follow that estimation. For instance, I might be distracted. So there's an error term, or what in a lot of machine learning literature is called the inverse temperature. There's some error due to me being distracted or due to me not wanting to lock into a specific strategy. But there's also the distinction of roles, right? If I am the person hiding, right, and I think that Anton is going to choose right, well, then I'm going to hide it in the left. While if I'm the matcher, and I think that Anton is going to hide the penny in the right, I'm going to choose right. So one thing is to estimate what we can expect the other to do. The other is to make a decision based on that. And we will see that those two parts will become two separate parts of the cognitive models that we're building. Just to tie it, I like to do these rants, sorry, but to tie it to all the statistical stuff that you learned, one of the problems with the frequentist statistic approach that most people use is that it conflates these two aspects. It says, just as we estimate a difference between two groups, right? A difference in learning from negative feedback between schizophrenia and patients with schizophrenia and controls that have no neuropsychiatric conditions, we at the same time make a binary decision as to whether this effect is significant or not. Right? The p-value threshold at 0.5 or wherever you prompt it. And there is no discussion about how the estimation process is giving you some information which might make different differences according to the context in which you're applying it. Right? So for instance, silly example, right? I might be developing a drug that helps people with psychotic disorders not to become addicted to gambling. And we test it and we see that it makes a difference, right? The participants who are taking placebo are becoming addicted to gambling in 5% of the cases, and the participants who are taking our drug are becoming addicted only in 1% of the cases. And if we look at the uncertainty, blah, 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 right? P-value below 0.5. So is this enough to make a meaningful decision as to whether we should start prescribing these drugs or even approving it for the market? Well, that actually depends on a bunch of other factors. For instance, which other drugs are available, how much they cost, which are the side effects of these drugs, which are the costs for the patient and the system of these side effects compared to the cost of gambling. And all of these factors can actually be formalized in a separate decision function. And so estimation and decisions should not be conflated, right? Because depending on the context, they will make different differences. The example I always give, and I gave it last time as well, so sorry for those of you who were there last week, is also if I develop a test or a series of questionnaires and practices that helps me diagnose people, or actually in English is autistic people, sorry, it's in Danish, it should be people with autism, in English, autistic people, according to preferences of the community, autistic people, I might have different costs for false positives and false negatives. As an educator, I might want to have as few false positives, false negatives as possible, right? Trying to give support to as many children as possible. As an administrator, I might, and I'm characterizing the problem, is more complex than that, but as an administrator, I might want to have as few false positives as possible because they're a waste of the resources that could help the children who actually have need for scaffolding, right? And this decision has nothing to do with the p-value. The p-value is a legitimate criterion, but the fact that it just comes out of the estimation is a problem because it doesn't separate these two issues, right? Good. One of the things that we didn't really manage to discuss during the class is what is the purpose of building this model? Right. Sometimes as we start looking at the matching pennies and maybe talking to the participants and maybe trying to figure out which models will fit best their behavior, we might realize that the best model that best fit Anton's behavior, sorry, Anton, is that, okay, he's going to play with a random bias the first 3 times, and then he's going to switch to win-stay-lose shift strategy for the next 5, and then he's going to count letters in the name of famous tennis players according to some rule and blah, blah, blah. And that is how Anton is going to play. And if we implement that specific cognitive modeling strategy, cognitive model, sorry, we describe exactly the data. What have we learned except having a fascinating insight into Anton's mind, right, and interests? Have we learned something useful about cognition? Right, describing the data perfectly is not necessarily the goal of cognitive modeling. The goal of cognitive modeling is to gain a better insight. So one of the things that we would learn from Anton in this case is that, oh, wait a second, people might actually switch strategy. And if we don't build that into our models, and that's hell, as a cognitive modeler, I can tell you that's really hell, we are mischaracterizing cognition, like the way that cognitive processes work. The fact that people actually change strategies, they use mixtures of strategies. But the fact that he's counting letters in tennis players' names is not really that useful for us, right? So sometimes we are deliberately choosing models that are not true. Well, technically, we never know which model is true, but we choose models that are deliberately more simple than what it would be required to describe exactly the data, because our goal is different, is to slowly, cumulatively, critically build better understanding of cognition. And that is something that we will try to discuss a few times, because throughout the examples, now we're going to start from the task, right? The matching pennies. We want to describe the cognitive processes coming from there. The next big example in a few weeks will actually do the opposite. We'll start from a theory of cognition and see whether certain experimental paradigm, which data we can access, can help us critically assess that theory. Good. Questions so far? Okay. So what we're trying to go beyond the analysis of performance and gain an insight on what goes on in your mind, to quote a very famous song. Models that could in principle tell us something more general about human cognition and what goes on than what goes on in this specific task. And we can actually skip that and say, we're going to start very simple, because we need to get into the whole idea of how we code these things, right? First, simulating the agents in R, and then inferring the parameter values and the likelihood of the model given the data. But with the same process, you can go very complex, right? So we'll be first modeling random biases, but it's very easy to say, what if this is really nothing but a Bayesian update on a trial by trial, which weights likelihood, so the current trial and the previous trials differently? What if it's a reinforcement learning mechanism? Blah, blah, blah. Okay. One warning, this is more to save face, but you'll see my code that has been written in a very pedagogical way, because it helps me writing it that way to show you all the steps. As you actually code, you'll probably be able to code much better than me in much more efficient ways. It's all for the pedagogy. And also, okay. I didn't write. Oh, it's probably in a later thing. But as I show you the code here, you don't need to write down the code because both the slides are going to be accessible, but also commented version of the codes will be part of the second course notes that I'll share probably after the class tomorrow. Okay. This is all made in the light of the assignment because the assignment is the way that I'm trying to force you to learn what I think is important. Yes.
Can you just quickly explain the purpose with the course will start? Is it like make points from the lecture or class or
Class.
class?
But as I show more and more code in the lectures, the code and the output is going to be there commented. It's more because as I teach this, so it has two purposes. One is for you, right? You don't need to sort of write down code, which is annoying. And sometimes they're going to keep passages in the code while lecturing because it's not useful for the pedagogy, but it might be useful to have it if you're having errors. Part is also for me because as I teach this course year after year, right, I have everything there commented and I remember what the heck that slide was about. But previous years I've found the course notes as useful as a resource, so I keep updating and adding stuff. Good. So the assignment, the first assignment for your portfolio reads like this. In this assignment, you have to create a document, Google Doc, Word, Markdown, whatever you run with, Overleaf, a very fancy LaTeX, whatever, and a GitHub repository. In the document, you need to describe two possible strategies to play the matching pennies. That is, two data generating processes that might be generating the matching pennies data. You have to include a discussion as to whether they include cognitive constraints, right? So given this is the very first assignment, you're very free to say, oh, I'm actually implementing a model that simply remembers all the previous trials and tries to estimate how likely my opponent is to play right. But I want you then to write a few words and say, this strategy is not including some cognitive constraints that we know are in place, blah, 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 right? Report the formalization of these strategies. That is a diagram and or lines of code. Actually, diagrams of your models are a very good skill to learn how to build because they make your papers, reports, whatever, much more understandable for whoever needs to read them, be it your boss or your censor. And you need to include plots of how these data generating processes fare against each other, since there's two, or against other baseline if you want. And a very brief discussion of what the plots allow you to understand. And then the document has to include a link to the GitHub repository, right? Because I want you to separate all the hard work of coding nicely and everything, and the fact that you'll always need to present your results in a separate product. Good. The GitHub repository must be linked in the document and must include all the code for the strategy implementation, simulation of agents, playing with those strategies, and visualizations of the plots. Is this clear? Good. Yes, of course. If you know how to build a DAG, yes, I'll show you DAGs of most of the models through the course, but even just a schematic that says, take the previous action from the opponent, put it in, take the feedback from the opponent, put it in, here is the rule, here is the output, right? Exactly. Whatever you think is most effective in communicating your model. Okay, I think I've ranted too much about this, but basically by formalizing, we can simulate results and understand implications of the models. By formalizing, we also get ready to do inverse inference. If these model were the true model and these are the data, which values would the parameters be? If the random bias is the true model and these are the data, what's the bias in the opponent? By formalizing, we can also plan analysis and program experiments, right? So imagine that we are really running these matching pennies as an experiment to figure out theory of mind or mixture of strategies or whatever in a population. It's by having agents that implement the different strategies, right? We can first of all set up an experimental script that makes the participants play against agents with pre-specified level of complexity, which can allow us to gauge the ways in which they're behaving. But also, we can use the data generated by our agents for doing all that sort of analysis planning, like power analysis, precision analysis, adaptive experimental design, procedure that allow us to plan in advance how many participants will we need, how many trials will we need, if we change the structure of the experiment so that the agent they're playing against is a 2-level recursion theory of mind versus a 3-level recursion theory of mind, how will that change our ability to reconstruct the parameter values? And also, programming is fun. Well, you're here at the master, so you have to agree now. Yes, the matching pennies game. So how do we start formalizing these agents? The first thing that we ask ourselves is, what does an agent need in order to play the matching pennies game? Right. So think about your ideas for models, right? Imagine that the agent is a black box, right? We're going to put stuff in the black box inside, but now the agent needs some input to play at any given point. Which kind of input does it need? Yes?
The information of whether the last pick led to success or not.
Yes, so this is two separate information, right? What they picked last and whether it was a success or not. So we need two kinds of inputs at the very least. Right, an input, which can be thought in different ways, right? It could be the previous choice or the opponent's previous choice. And then the feedback. Or my previous choice and your previous choice. They're all like, as long as I have two of these two, I can reconstruct the third. Yes? No? Good. Then we need an internal mechanism. We need to open up the black box and put something in there that takes the input and turns that into a decision. Right? I know this is very basic, but going through the step one by one helps thinking how to do these things. And it will apply to more complex models. Right? A prediction of what to play, right? An estimation of what the other is more likely to play. And then a decision mechanism that turns the prediction into an actual choice, which in our case is binomial, right? You can play right or left. Yes?
Just to understand, is that last step, is that what you were talking about before with error and decision function?
For instance, yes. Yeah. So the idea is that this one is just going to make a prediction about what you're going to play. And this one is turning that prediction into an action, if you want. Which, for instance, if I'm the matcher, it might be the opposite. If I'm the one who has to guess, it could be the same, but it could also have some, oh, I'm gonna add some randomness to the to what I do because I know that the other is trying to predict me, right?
Yeah, so it's kind of the first part is the
Estimation.
Yeah, you make an estimation.
Yeah.
And then you say, okay, but this is what I'm going to use it for.
Exactly.
And that might differ depending on the context.
Yes. And so, for instance, right, even the decision mechanism could be quite complex. So when I'm playing with my kids, right, if I'm winning too often, I might actually start letting them win a few more times to keep the game fun, right? And so implementing that in the decision mechanism is not as easy as to say, pick if it's above 0.5, pick 1, if it's below 0.5, pick 0, right? But these are the two logical parts. Questions on that? Does it make sense? Good. And an output, the choice. Does this actually, this is because the decision-making course keeps changing for good. But does this resonate with what you've been doing in decision-making? Good. Okay, then we go from these logical structure, we start coding it in a functional way. Are you all familiar with the functional programming versus object-oriented programming distinction? Some of you, not everybody. The basic idea is that if you program, most people who program R will program things in terms of functions, right? So we're going to have a function of the agents that takes an input and returns an output. People who program in Python, they tend to program in, or not all of them, but many, in terms of object-oriented programming, which means that they create agents which have internal properties that can inherit strategies, that can store things within the agent. And then they have functions that apply to the object. For path dependencies, I am much more familiar with R, and it's easier for me to sort of figure out what I can learn and what I need to learn. So I'm going to teach you in the R way of doing things. Just know that it would be relatively easy to turn it into an object-oriented approach if you were coding in Python. The good thing with Python is that you can also do it in functions. But yes, this is what we're going to do. Here was the comment that I was searching before. Okay, so the idea is that we have an output, which is generated by an agent function, which has some inputs and some parameters. Right. This is how a function of an agent looks like. So if we want to turn it into our code, right, the way that we do that is we define a function. And this is just me, but whenever I define a function, I always end it with _f. So I remember it's a function. It's being kind to my future self in 30 minutes when I'll forget. We tell it that it's a function. And then we need to specify some input and parameters. Right. So if we're programming a random agent, right? Random agent function, same as before, we say it's a function. And then what we have is we have the input, and the internal parameter is simply the bias, right? How often it picks right or left. And so really there is no estimation, right? Because the random bias agent is not taking the other into account. Does that make sense? So the only thing that we need to do to have a choice is to sample from a binomial distribution, R binom, one time, right? Only one choice, right? Because binomials can be how many times out of 10 trials, according to a given bias, right? And then return that choice. I know it's very basic for some of you. We're going slow. And then given, so I like to keep these because many other agents will need the input, but since it's not really using the input, we could even just remove it. Does this all make sense? I know that not everybody has done the bachelor, so I need to sort of bring everybody to the same level. Does this make sense to all of you? Good. So now we coded our agent. The thing that we need to do all the time, even with very simple agents, is trying to figure out what the heck it's doing when we stress test it, when we put it in different conditions. Right, so we define a rate. And then we ran the function with that rate and save the choice. Right. Again, sorry for these being very basic, but here is how we define the function. Once we defined and made it run, it's in the memory of your R session. And then we can call it and run it. And then we can display the output that way. So what is the agent doing? Here is some code to visualize it. I'm going to use tidyverse because I'm that kind of person. In R, for those of you who are not part of the R discourse, there's the really big fans of base R, which requires you to know what you're doing, but it's very flexible. And the fans of tidyverse, which is very pedagogical, very structured, is not always faster, and sometimes it narrows your options, but it's so nice for teaching. So you did the statistical rethinking handbook, right? In methods 4, Richard is a big fan of base R, and it shows through. And I'm a big fan of tidyverse, and we often make fun of each other. We define how many trials, 120, just because. We create an empty vector for the random choice. We repeat NA as many times as the trials. And then we say that for T in the sequence of trials, this will generate a vector that has all the numbers between 1 and 120. The random choice at trial T is produced by the random agent function with rate. And then, since we use tidyverse, tidyverse really likes data frames that now are called tuples. And so we say that there is a data frame called D1, which has a column called trial with a sequence of trials, and a column of choices with a sequence of random choices, which allows us to plot it. In tidyverse, the choice of plotting device is the ggplot, grammar of graphs plot, that tries to make plotting things as logical as possible. We give it the data frame, D1. We give the aesthetics, so what's on the x-axis and y-axis, what determines the colors, blah, 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 which is x equal trial, y equal choice. And then we need to represent these dots as the choice changes on a trial by trial base. We're going to put a line. And then, because I'm that kind of nerd, I don't like the gray background, and I say theme classic. And then we look at it, P1, display the plot. I promise you it's going to get more complex. I just want every step to be in place, right? Isn't that a beautiful visualization? What's going on there? Yes?
Plotting the choice of each trial, which means that it can only be 1 and 0.
Yes.
If you get a linear or connected to those by lines, it just goes up and down.
Yes. Is it giving you any information? Yes.
It's giving me the information that there doesn't seem to be that much of a pattern.
Yes. So it's telling us basically that there's roughly as many choices at 1 left or right, whatever one is, as there are in the other dimension, right? And actually, I didn't provide a step, but the step is we code we code left and right as 0 and 1s, because 0 and 1s are easy to deal with when we use programming languages, right? And when we do models. Okay, so this is a terrible visualization, but sometimes you just want to start somewhere. And let me see. Then after the break, I'll ask you to come up with a better one. But let's keep on with these for a second. What about different rates, right? Now we've seen rate of 0.5. We want to make sure that when we give the function a rate of 0.1, it mostly goes 0. And when we give a rate of 0.9, it mostly goes 1. Right? These sanity checks might seem trivial are super important. They're going to save your life, academic life, a bunch of time. Or actually, they're going to ruin your careers because suddenly all your results are going to be based on an artifact. But they're going to save you a lot of time when you're trying to debug. So you don't always have to write an email to Malte and say, Malte, come and save me, as I do. Yes. So here is a loop. You might have opinions about loops. We'll do parallelization at a later class. We say a rate that is in a sequence between 0 and 1 in steps of 0.1. So it's the same function as before, but now I'm specifying not integers, otherwise it would just be 0 and 1, but actually all the numbers that are 0.1 from 0, and then 0.1 from that number, and then 0.1 from that number until it reaches 1. We have a random choice vector, just like before. We have our 14, the sequence of trial, generation of the random choice, given the random agent and the rate, just as before. We have a temporary table where we save these data. A column with trial, a column with choice, and the rate, so we remember which rate it was. And then, again, this is my own way of thinking through that in a pedagogical way. There's better ways and faster way of doing that, but this works. If D1 already exists, then bind, so put below D1 temp. If it doesn't exist, initializes with temp. Then go to the next rate and run it again. Does that make sense? Good. Then we do ggplot, where we use that overall table, trial on the x-axis, choice on the y-axis, geom line, and then we create separate facets per each rate so we can see what's the impact of choosing a different rate. Think classic. We visualize it, and this is how it looks like. Anybody wants to comment before we take a break? Yes, Malte?
It's kind of hard to tell the difference between different rates.
Yes.
Between, let's say, 0.3 and 0.7, I couldn't tell the difference without really thinking about it.
Exactly. So this is a bad visualization, right? But it seems to work, right? It's clearly that 0.1 and 0.9 are different. Yeah. Let's take a 10 minutes break, and then we'll figure out a better visualization together. Visualizing your models is a key skill. So we're starting, and we're going to do it again and again and again, also going through bad visualization. Yeah. Zero something. Plus, you know, we're in a train, someone, then you see that no one like an hour, and then you're already like it's either going to be taken
I like it. Because it justifies. It justifies a lot of people are like, hey, okay, so.
I think considering it's gonna take at least 2 years. Because these guys are closing all.
Was you gonna, you would still see how fast it was up, but you still see how fast.
Yeah, I wonder how it's gonna like close.
How fast is it not?
Okay, let's start again. Good. So if you remember, we just left off with this terrible visualization of the impact of different rates on the choices of left 0 or right 1 in the matching pennies game. You have better ideas. How would you go making a better plot? Yes?
It's a little bit hard to see what the proportion between choices are. And right now, maybe the shifting between left and right
Mm-hmm.
as interesting. So all the lines are not down are be confusing.
Yep.
What I mean is we could just plug points.
Okay, if you only had points, yes, that would be potentially an improvement. It's still gonna be pretty hard, especially when you're close to 0.5, like 0.7 and 0.3. Yes? Which one you said? Bar plots. Oh, how many times it chooses. Yeah. That would work, except that the number of trials that we want to run our experiment might be very crucial, and we want to keep that. Yes. Yeah.
Make a color bar for each, like the horizontal segment bar for
Mhm.
the first one trial, and then there's 2 colors. It's one for one.
Yeah. So that wouldn't it? Yeah, that's another way of looking at it that puts basically colored bars, and then that's more easy to see than these very fast up and down. You have a point? No, Malte?
One that's specific to this model that we are studying right now would be a cumulative mean.
Yes.
You keep a little bit of the temporal aspects and you keep a little bit of the different rates, probably.
So the idea is we see as the trials progress, where the average rate of right versus left changes. And that's what I had thought. So I'm just going to go with that. And we can discuss whether this makes more sense. So how do we do that? We take our data frame or table. We group it by rate because we don't want to generalize, make calculation across rates. They're separate agents if you want. And then we create with mutate a cumulative rate variable, which has a cumulative sum of choice. What is a cumulative sum? It means that in the first trial, it only takes the choice. In the second trial, it sums up the first and the second choice. In the third trial, it sums up the first, second, and third choice, and so on and so forth, divided how many choices have been made so far. Right, so the first trial, it's the choice divided 1. In the second trial, it's the sum of the first and the second choice divided 2. In the third, the sum of 1, 2, and 3 divided 3. Right? And then we do another ggplot where we still have the trials as the x-axis, but the cumulative rate as the y-axis. We still do the geometric line. We facet wrap by rate. That is, we create different panels by rate. We still remove the silly gray background. And then as a reference, we're doing something new. That is, we're adding a horizontal line, H line, at 0.5, the random chance rate of 0.5 on the y-axis, and we make it dashed. So we have a reference of where it would be a perfectly random rate. Right, and then we visualize it. And this is how it looks like. Is it better? It might still be kind of tricky to compare 0.3 and 0.7, right? How would you solve that? Yes?
Instead of faceting, maybe you just use a color.
Yes. So we color by rate and we group by rate. So we're sure that it makes different lines for each of the rates. We remove the facet wrap. The rest is unchanged. And here I left rate as a continuous. If you make it as a factor, it chooses much more different colors. But you start seeing the different agents playing with different rates overlaid to each other. What is this telling you? Right? Yeah.
Or it tells us that there's a certain amount of trials for the cumulative rate to approach the rate that was previously mentioned.
Yeah. So in a sense that if we are conceptualizing our agents as random bias agents, we cannot have them play, let's say, 25 trials and hope that we can infer correctly which rate they are using. Right? Of course, we can make a formal test of that, but already this quick and dirty visualization, it tells us it takes quite some trials to separate the behavior of these different agents. And now we're running only one agent per rate. If we were to run 10 agents per rate, it would be even more messy, right? Which again, at these level of modeling might seem trivial, but as we get with more and more complex models, how many trials you need to separate behaviors, or what does it mean to have a low learning rate for positive feedback and a medium learning rate for negative feedback versus the opposite, right? How is it gonna be showing up? It's non-trivial, right? So we learn to do things also in the simple models. Questions? Okay, what if we now want to start including cognitive constraints? Right. So for instance, does it make sense to add memory to these models?
Since it's not making a choice based on the previous choices.
Yeah. Yes, it doesn't make sense in this specific model, right? If we wanted to add memory, right, it shouldn't be a choice just determined by bias, but it should be a choice where we might still have a bias, but also an impact of the previous choices of the other. And I think, so for instance, we could drop the random bias part and then just say, well, actually, what if this agent is taking as input the previous trials, given a certain memory span, and then makes an average based on those trials. That corresponds to its rate in that given trial. In the next trial, it's going to make a new average because the window has moved of 1, right? The previous 5 trials, or magical number 7, right? The previous 7 trials now have shifted of 1, right? Or we could do an optimal Bayesian update, right? Given your previous rate and what I see now, right? How do I combine these 2 pieces of information, given them equal weight? Or a weighted Bayesian update, which are all stuff that we will cover later in the course, where you might give more weight to the past than to the just last trial, because there might be noise in trial by trial choice, right? Or we might have reinforcement learning, right? And again, that's something that we'll probably cover at a later stage. But the general idea is that it's error-driven learning, where at any point in time, expected value is attributed to the choice of right, and 1 minus that is attributed to the choice of left in this specific case. And that value is updated on a trial by trial base, taking the previous value and then adding the predictive error times a learning rate. What is the predictive error? And then we'll get back to the learning rate. The predictive error is the reward in the previous trial, subtracting from that the expected value. Meaning that if I was already expected to win by playing right, and I win by playing right, the prediction error is 0, right? That I'm not changing my belief because my belief just got met by reality, right? While in this specific case, it's easy, right? Because there's only 0 and 1s. If I get a reward of 0 and I was expecting to win, my predictive error is -1. But if we simply were to apply the predictive error to the previous value, that is, learning was 1, what we would do is we would completely change our mind, right? Because -1, if this was 1, right, goes to 0. So now we should always play left, because the expected value of playing right is 0. 1 minus that is the expected value of playing left. I should play left, right? This is a suboptimal strategy, especially noisy environments. So usually we have a learning rate that's below 1. So we're not completely driven by the previous trial, right? The update is only a portion of the predictive error. We change our belief towards left by an amount that depends on the learning rate. If the learning rate is high, by a lot. If the learning rate is low, by a little. Does that make sense? Which mathematically is very equivalent to weighted Bayesian update, where depending on the learning rate, you might have higher or lower weight on the past, or is very close to a Kalman filter, where you keep updating your estimation of the means given the feedback that you get on a trial by trial basis. But again, that's for later. However, in the current model, the random bias model that we're using, does it make sense to add errors, right? The random bias agent might be biased towards right, let's say, but could it make errors, right? As it decides to go right, or then pushes the wrong button, for instance. Is this something that's meaningful? So I can see some people nodding. I can see some people being baffled. And I think you're both right. In the sense that, yes, it makes sense because we can put the agent making a choice, and then put a second passage that says, but in 10% of the cases, sample again, right? From a distribution with a rate of 0.5, which is useful for us when we're going to build more complex models and we want to include an error term, right? Where you might be keeping track of the other moving average using a reinforcement learning or a hierarchical Gaussian filter system, but you might include a temperature that is your tendency not to always follow what the estimation is telling you to do, right? It makes us a bit baffled because this is already a random process, right? And if we add an error, what does that make to the random process? And that's where visualizations help us. So, for instance, we can say the random agent, and again, there's more efficient ways of coding this. I think this is pedagogical. Is our function where it takes a rate and a noise level, a rate of errors, if you want. It makes the choice exactly like before, but if sampling from the noise, a binomial distribution with a rate equal to the noise, and we get a 1, then we sample from a completely random distribution. It's a bit of a mind F-U-C-K. But it is a way of conceptualizing this noise, right? So we have a choice, however, we got there, and then whenever the noise tells us to, we simply replace it with a choice at random. Of course, it doesn't work very well if this is 0.5. And we return the choice. Does this make sense logically? Statistically, if you're doing maximum likelihood, so if you don't have priors, a combination of two binomial distributions is impossible to separate. But we're Bayesian, so we can, and we'll see how to do that at a later stage. So we do a data frame for a bunch of levels of noise from 0 to 0.5 in steps of 0.1 for a sequence of rates from these 0 to 1 in steps of 0.1. We create a vector for the random choice. We loop through each of the trials. But now instead of having the random agent function, we have the random agent noise function, and we feed the rate and the noise. We create our temporary data frame with the trials, the choice, the rate that we're using in this specific loop, and the noise that we're using in this specific loop. And then we do that trick to keep on appending the data frame. So by doing this, and again, we'll see when we parallelize, there are better ways of doing this, but by doing this, we say for each level of noise, try all the levels of rate, right? So we have the full combination. Does this make sense? Then we do our trick where we group by this time by rate and noise because we don't want to mix all the levels of noise within the same rate, right? We want to keep all the combinations separate. We calculate our cumulative rate. We do the ggplot. That's exactly like before, the overlaid one, but now we're phase-it wrapping it by noise. So we get a bunch of overlaid plots, one panel per each level of noise, and then we can see how difficult it becomes discriminating between the rates. And then we visualize it. Okay, this is how it looks like. What do you see there? Remember, in each plot, there's all the levels of rate, but a fixed level of noise. Here there is no noise. Here there is the maximum level of noise that we identified in the or that we defined in the simulation. So this is what you already saw before. Yes, Clara?
Yeah, so it seems that that makes a lot of sense that if you add a lot of noise, you're gonna like push all of the choices against more and more randomness.
Yes.
So you won't get these types of like straight lines of people doing almost always like left hand or right hand, but you will get like this switching up and down more.
Yes, exactly. Right. We see a very clear shrinkage towards the center. We also see, maybe not from there, but that the trial number at which the pattern starts separating gets longer and longer, gets higher and higher, right? The more noise you have, the harder it is to discriminate between the behaviors, right? Because there's a lot of noise, right? It makes sense. These, again, might seem trivial, but it's something that people always forget when they're running power analysis, when they're running predictions of how their participants are going to behave, when they're making statistical models and assuming that the data that they have is true measures of the underlying construct. Making sure that every time that we run this simulation, we add some noise and we observe how much it fucks up our behavior, our data, is actually very healthy. It impacts also your power analysis if you want to run that sort of things, where you say, well, in order for these economically feasible amount of participants to reliably give us the signal that we want, given an expected effect size of blah and blah, well, we need to assume that the noise is below this level, right? If we don't, then, well, it's a problem. But on the other hand, it gives you a tool. You can say, well, I don't have more money for more participants. What if I actually spend some time working on better measures to reduce the noise, right? So for instance, here, it could be make a better interface that helps people not make mistakes and keep focused on the task. So for instance, you could have like a computer game with some nice visuals that keep people attentive and so on. Also, well, there is a whole thing about measurement models, which we might touch at a later stage in the course, but also in industrial applications of data science, people design questionnaires. And sometimes they need sensitive information like political beliefs or sexual orientation or stuff like that, which might be problematic if it leaked. So a common strategy that is used when administering those questionnaires is that at random, in a way that is not recorded, some of these questions for some of the participants get replaced with which of these two figures do you like better? And there's a blue circle and a turquoise triangle. Right. And then people choose the one or the other, or how much they like one, whatever, according to the format of the original question. And that is the answer that get recorded with that specific question. Not with the triangles and squares, but with the original question. So that there is always plausible deniability and no legal value for those leakages and for those data if they leak, and no way of pointing fingers. Of course, people might point fingers anyway, but it is one of the strategies that's used. And given that then you introduce this kind of noise into your measurements, you need to plan for that in advance, right? So noise has very concrete applications to scenarios that you might have to deal with in the future, right? Okay, now we've done the easy part. So what about a responsive agent, right? That agent was easy, right? It was just behaving in its own way, no matter what happened outside. But as you played the game, you had probably a very clear phenomenological experience that the other was reacting to you, right? And that you were reacting to the other. So we need to have that in our model. Let's try to formalize it with the win, stay, lose, shift rule, right? Just to give you an example of the workflow. Now we create a new function. It's the WSLS agent function. Define it as a function. It takes the previous choice and the feedback. Right. We could make it work with the opponent previous choice and your own choice, with the opponent previous choice and the feedback. Any two work. If the feedback is 1, then we stay. My current choice is the same as the previous choice. If the feedback is 0, if we lost, my choice is the opposite, 1 minus previous choice. If the previous choice was 0, 1 minus 0 is 1, opposite choice. If the previous choice is 1, 1 minus 1 is 0, opposite choice. Right? That's where I was saying that 0 and 1s instead of left and right become very convenient because we can do all these sort of tricks. And then we return that choice. Then what we can do is we can see what happens, right? Previous choice is 1, feedback is 0. What's going to be saved as a win, stay, lose, shift choice? What's the output? Yes, exactly. We played right, we lost, we're going to play left. And we set up the sequence. If we want this agent to play against a random agent, we need to define the rate of the random agent, 0.7. We create a vector for the self choices and a vector for the other choices. First choice is random, right? You might have a specific bias, but we can initialize it by being random. So for each of the trials, the other is a random agent, right? So plays as a random agent with a rate that we predefined. But our win, stay, lose, shift from the second trial, when it has seen what the other is doing, will say, well, if the previous own choice is equal to the previous other choice, the feedback is 1. Right? The random bias agent is the one hiding, and the win, stay, lose, shift agent is the one guessing. Otherwise, the feedback is 0. And then the choice is defined by the win, stay, lose, shift agent function with the previous self choice and the feedback. Does that make sense? Okay. Please ask if you have questions. There's no stupid question, right? How do we visualize that? Well, we can do the table where we take the self and the other, the trials, and then we just calculate the feedback from the 2 vectors because I didn't save it. Otherwise, I could have saved it. We do the ggplot, and where we have in red the self choices, in blue the other choices, because I thought it was kind of neat. Still a bad representation, but it starts getting more aesthetically pleasing. If we look at performance, right, we calculate the feedback that the person is doing using a cumulative rate. And we can say that initially it swings, and then it starts stabilizing with the win, stay, lose, shift performing better than the random bias agent. Why is that? Yes?
Because there's a dependency, well, because there is a bias in the random bias A.
Yes.
Because it has a 70% chance of picking one side, it's just pick that side, and the Wednesday loose shift also pick that side. It's going to keep picking that and have a 70% chance of winning the next round.
Good. Exactly. Right. Again, these things might seem initially easy, but visualizing this and asking this question is a really good practice as we increase the complexity of the model. Good. If we change the rate of the random agent, this is how the performance of the win-stay-lose shift is going to change. And so as Malte was pointing to, the more stable the random agent is, the higher the performance we can get. Right? The closer the random agent gets to chance, the more the win-stay-lose shift strategy simply doesn't work. Does that make sense? Generally, we'll see that if an agent plays a chance, you cannot win. Okay, what if we want the agent to play against the win-stay-lose shift? So we have a win-stay-lose shift playing against a win-stay-lose shift. What do you think is going to happen? Yes?
They could get like asynchronous, so there's just one that's winning at the time.
Could it? Because if you're winning, you're staying. And if I'm losing, I'm changing. And then I win and you lose. Right? Since our incentives are completely misaligned.
Yeah, I'm just imagining that I would be one step ahead.
Mhm.
But that's not.
Well, that would be a different model. Yes.
It also depends on if you code the shifting as switching to the other thing or as rolling another thing.
Yeah. Yes, but now we are saying just win-stay-lose shift fixed. Right. Okay, so we can see it. Again, we code the self, we code the other, we pick at random the first time because we have no feedback to base it on. From the second trial, we say if the previous choice is equal to the other, feedback is 1, otherwise it's 0. And then we fit the previous self choice and the feedback to the agent for the self, and we do the same for the other agent. Right? The first agent gets the self at previous trial. The other agent gets the other at previous trial. The first agent gets the feedback as it is. The other agent gets the opposite of the feedback, because if one wins, the other loses. Right? There are cooperative games that we could simulate where they would get the same feedback. Right? But in this case, if you win, I lose. Right? We do. Yeah, this should start to feel boring, right? The table with the self, the other, the trials, the feedback. There is no parameters, right? We don't have any bias or any noise at this stage. And then we start plotting. This is the win-stay-lose shift versus random bias that we've seen before. And this is the win-stay-lose shift versus win-stay-lose shift, which becomes perfectly symmetric, right? Perfectly regular and symmetric. If we look at performance, I just thought it was cool. It's terrible visualization, but it's kind of cool. I think they call it accidental art. And this is what the performance looked like, right? So here they're simply alternating all the time. When we use the cumulative rate, we see that they're converging at 0.5. And you can run this a million times. It's completely deterministic because there is no noise parameter. And so that's what you're going to get all the time. What about think we're getting towards the end of today. So does memory make sense? Well, not within the win-stay-lose shift. Right. We would have to shift to a different kind of model, just like if we wanted to add memory to the random bias, we would have to shift to a different kind of model. Here, the memory is perfect of the previous trial and no further. If we want to add errors, there's at least two ways of doing that. Here, I'm showing you a way that's perfectly symmetric to how we added it before. Right, we have the function that's exactly as before in choosing the same as the previous choice if we won, the opposite of the previous choice if we lost. But we add a random sampling from a binomial distribution with a rate equal to the level of noise. If we sample a 1, we pick at random. And then that starts breaking the symmetry of our agents, right? Because there's this noise that messes up the behavior. And the performance in the long run might converge to 0.5, but the noise will always push it away. So it's going to converge and then move away, and then converge and then move away, right? And these moving away, if we just keep the cumulative performance from the start, they'll keep on becoming smaller and smaller, right? What would be another way of implementing an error? Implementing a probabilistic process instead of a deterministic process. I know you, yeah.
The strategy shift?
Well, you could have a strategy shift, but I'm just saying, just keeping the win-stay-lose shift as a general framework. Now it's deterministic, right? We added potentially some noise with this specific manipulation, but we could have done something different to introduce a probabilistic dimension to this.
So not changing the strategy when you have to change the strategy?
Yeah, exactly. For instance,
Yeah.
how would you do that?
So if the agent, if you win, you might just still change your strategy randomly? Because
Yeah, how would you define that?
so if win, there is a X% of chance for you to shift.
Yes. So we're going to add a weight or a parameter to the probability of shifting when winning. And maybe the same parameter, maybe a different parameter to the probability of, sorry, we're going to put a weight or parameter on the probability of staying if winning. So it's not 100%, but it could be 0.9, 0.8, whatever. And the same parameter or a different parameter to the probability of shifting if losing. Yes? Because what we're doing right now is just symmetric noise, right? We are just saying sometimes the person pushes it right, like just gets distracted and might push the right one or the left one randomly. Now we're saying actually the strategy in itself is probabilistic. The impact might be the same if we keep it symmetric, but if we start making it asymmetric, then it will have a different impact than just a random error. And that is something that as cognitive scientists, we should be aware of, because you know that people tend to react much more strongly to punishment than to reward. In these paradigms. In learning, it seems to be the opposite, right? People tend to learn less from punishment than from reward. But in these paradigms with small electric shocks or small losses and small wins or small, I don't know, sips of fruit juice, whatever, beers, then the punishment seems to change in the short run the behavior much more strongly. So separating those two probabilities makes sense from a cognitive perspective. Does that make sense? Right, and you can see that even with these very simple models, as soon as we start thinking about them, there is lots of complexity that we can build in. Yay! Okay, the next step, of course, would be to scale it up to 100 agents, right? Because now we've ran one agent in each combination of the values. And in all the models in which there is a probabilistic dimension, we need to run more agents in order to see what's the range of behaviors, right? And these could be clones or populations. What's our clones? Clones are agents that have exactly the same parameter values. 100 agents with a rate of 0.7, 100 agents with a noise of 0.1. A population of agents instead is something that you should know from the mixed effects or multi-level or hierarchical models. The idea that there is an underlying parameter of the population, let's say a rate of 0.7, but individuals might vary a bit from that. Right? So the rate is sampled from a normal distribution with a rate of 0.7 and a standard deviation of 0.05, for instance, right? So they can vary. And that will give you different results. You can loop through 100 pairs of agents, or you can make a function that simulates and saves a combination of one pair of agents and then parallelize using FIR, and we'll see that in a later lecture. For the class, what we're going to do tomorrow, yes, it's 2 strategies. Describe 2 strategies, pick up whatever you want, formalize them in code, set them to play against random agent and win-stay-lose shift agent, or against each other if you want. Run 120 trials, just so we have comparable results across the different groups, and 100 agents of each of your strategies. Visualize and comment on the simulation. Once that is done, that's your portfolio 1. Right. Usually, but we can negotiate it on a running base. What I do is, during the class, there is a specific class or sets of classes that's dedicated to a portfolio assignment. And if you send me your assignment a week after, let's say, so if tomorrow it's about portfolio 1, so next Thursday, if you send it to me, then I have the time to sort of go through them and then present you a collective feedback. If you don't, that's absolutely not a problem. Your assignment is not included in the collective feedback because I need to move on, right? Good. If you have no ideas about which strategies you want to implement, given that I want at this stage to learn the process, the same that we implemented are fine, just do not copy and paste the code, try to reconstruct it. You can implement the probabilistic win-stay-lose shift, right? You can implement a memory strategy. If you feel daring, you can implement the reinforcement learning, right? It's not crucial at this stage how complex the model that you want to implement is, just that you get the good basis of the process. Because in the next, not in assignment 2, but in assignment 3 and 4, we will repeat the process, but with much more complex models. So you can sate your thirst for complexity at that point. And then next week, we will start opening up Stan and inverting the models. That is, writing the model in Stan so that if there are parameters, we can infer the values of the parameters from the data. And that's all of it for today. And enjoy it, because it's very rarely I end up 2 minutes in advance.